This is Julia Santagata. I am one of the automation managers here at Rumsey Electric, and thank you everybody for spending some time with us today. As you're probably aware at this point, this is one of an ongoing series of technical webinars that the Rumsey Automation Group is hosting every Tuesday at 11:30. We appreciate you hopping on. Today's speaker is Rick Archer, talking about regeneration and VFD.
Thanks, Julia. As Julia mentioned, I'm Rick Archer. I'm one of the drive specialists at Rumsey. We have three of us full-time. Roberts is on the call as well. So if you do have any questions and you want to type it into the chat, feel free. Hopefully you can answer it. If not, we'll get to it at the end. So today I'm going to be covering regeneration and breaking of VFDs with the title of Stop It, which is something I used to holler a lot at my four daughters. Again, I'm a drive specialist. I've been with this role for 14 plus years. Spent 30 plus years in industrial automation, various manufacturing sites. And then prior to that, I was in the U.S. Navy for 6 years, worked on the missile system. And you can see by the pictures, I'm an avid motorcyclist. I actually race. I'm still waiting for Rockwell to give me a sponsorship check. They have not to this date, but I still use one of their drive numbers, 753, as my nameplate. We've done quite a few webinars based around VFDs. The first one was correcting harmonic distortion. We did some installation considerations. We went into line side protection. We went into protecting your motor or load side. And we also went over the software. When you get this presentation in the slide deck, those are available on YouTube, and there you can just hit the link there and watch them at your leisure. It's going to be a couple technical resources that I reference throughout the presentation. The PFlex AT001, it's the PowerFlex Dynamic Braking Resistor Calculator. The other one's Drives-AT002, and drives in common bus configurations. And then there's a couple general purpose drives IN001 and drives AT003. And you'll get links to those as well. First thing I want to go over a basic diagram in the power circuit of when a VFD is motoring. And you can see in the right up, the converter on the left side changes the three-phase AC into DC. When the diodes are forward biased or when the converter is forward biased, current flows unidirectionally through the converter. That DC voltage goes through the link choke, gets filtered by the capacitors, and is applied to the inverter section of the drive. In the inverter section, there's 6 transistors, insulated gate bipolar transistors, commonly referred to as IGBTs, and 6 diodes in the inverter section. When we're motoring, the diodes are reverse biased, and when regenerating, they're forward biased. And the IGBTs or transistors are used for motoring, but are not used during regeneration. When we go into a regeneration mode, which happens when the motor turns faster than the synchronous or applied speed that we're trying to tell it to go, or when you're braking. During regeneration, the converter is reverse biased because it can't handle the bus voltage or extra power without damage. And during regeneration, the diodes on the IGBTs around the IGBTs, which we call flyback diodes, they can allow a certain amount of energy to go through. If it's too much, damage can occur to the converter, inverter, or the capacitors. In addition to the possible drive damage, the laws of physics say energy can never be lost or gained. So we need to handle regenerative energy somehow. There's 2 main types of regenerative energy. It's rotational, when it occurs during normal deceleration of a motor. Overhauling, which is continuous regeneration caused by the load on the motor. and overhaul is the most severe type of regeneration. When you're looking at an application where you may need to take into account, it's important to understand the difference between the two types of regeneration and how to manage the DC bus. If the change of the DC bus voltage is not managed in a regenerative application, you'll get an overvoltage fault. An overvoltage fault on our drives is indicated by an F4, and on a 480 volt drive, it happens is 820 volts DC. So if you start getting overvoltage faults and you think it's a regenerative application, how do you handle that? And you can put a dynamic brake unit, and dynamic brakes come in several forms. They got a bunch of different names. You'll hear them called different things. And I have a list here of a few things that you'll hear. You may hear it called a chopper. You may hear it just called a dynamic brake. Some people just call it a DB resistor, shunt regulator, snubber. And today, which has been since about probably the early 2000s, you may hear it just called a brake IGBT or seventh IGBT. And when you hear that, we put an IGBT and the DC bus monitoring circuitry right within the drive. You can also hear regeneration unit or active front end, and they're both very effective in handling regenerated energy. You'll use that for regen braking. And then you may also hear common DC bus, and that's when multiple VFDs are sharing the regenerative energy. So no matter what you call it, it's a dynamic brake or a chopper circuit or seventh IGBT or any of those things I listed. I'll use 460 or 480 volt as an example, but typically the DC bus runs around 650 volts DC on the bus for normal operation. And the dynamic brake unit, whether it's internal to the drive or external, is just sitting there doing nothing but monitoring. And you can see up on the right side with the red highlight, that's an example of an external chopper or dynamic brake unit. During regen, the control circuits inside the dynamic brake sense a voltage rise on the DC bus. When the bus reaches 750 volts DC, it turns on the IGBT, causing the current flow through the brake resistor and start bleeding off that regenerative energy. Current flow through the resistor causes voltage to dissipate or burn off. It will stay on until the voltage on the bus drops back down to approximately 735 volts DC. If it starts going back up, as soon as it reaches 750 again, it will turn back on the IGBT and start bleeding off that energy. Again, this is 460 volt example for our drives that run in 230 or 575. The only thing that changes turn on and turn off voltages. So when we talk about braking, there's a few different ways. Rotational regeneration is best handled by choosing the appropriate stopping means based on the requirements of the application. And you can see on the chart, there's 5 ways to stop a motor: coast to stop, ramp to stop, injection braking, dynamic braking, and regenerative braking. And you can see coast to stop being the farthest to the right based on time, regenerative being the quickest. And I'll go into detail on each one of these. Coast to stop is when the application doesn't require any stopping means. As soon as you tell the drive to stop, the motor is just coast to a stop, and the friction of the motor shaft or the application, if you have a mechanical advantage, the mechanical energy on the motor, the energy is dissipated by friction in the form of heat, so no regenerative energy is going back into the drive. A ramp to stop, which is very common for a lot of applications, is when a relatively long period of time to stop the motor is acceptable for the application. The drive ramps the speed of the motor down slowly and absorbs a small amount through those flyback diodes that I talked about and the capacitors. And again, the drive can handle small levels of regeneration without any additional devices. And it may not be suitable for use with all applications. If you put your decel time to, 0.1 second, and you start seeing overvoltage faults or something, it may indicate you need to handle that regenerative energy outside of what the drive can handle. Next on the quicker stopping is injection braking and flux braking. And these slow a motor down quicker than the first two. Injection braking pumps DC in the motor, causing it to do the actual braking. And flux braking, the flux current or magnetizing current is increased in the motor by the drive, causing the motor to do the braking. And it's actually the exact opposite of field weakening. I put this summary in here because I personally do not use this type of braking in most applications, purely because of what this summary says. These types of braking dump most of the stored energy into the motor by intentionally causing high losses in the motor. Neither provides a controlled stop time, and not having complete control of the motor may be a safety issue in some applications. Using these types of braking may damage the motor over time. That's the main reason I don't use this type of braking often. And you should use extreme caution when using these methods of braking, and only for a relatively short duration. And if you make that duration too long, I can guarantee you get hardware overcurrent. I had that one application that they had put DC braking as their preferred method of stopping, and they kept getting hardware overcurrent. It's because they had their DC braking on too long. Dynamic braking is used when a relatively short braking time is required. And this method of stopping needs additional equipment, the 7th IGBT, and a resistor or a dynamic brake or a brake chopper. When using this method of stopping or braking, the regenerative energy is burned off in the form of heat through those braking resistors. This method does a great job of eliminating the relatively large rotational regenerative energy in short periods of time. It can also be used for overhauling regenerative applications, but it's not necessarily the most cost effective. Dynamic braking is probably the most common that we run into. And we sell the dynamic brakes in most applications. It does just fine when it's intermittent braking. If you remember back to when I said there's two types, rotational and overhauling. Overhauling loads are when the motor is being forced to go faster than we're telling it to go, or there's some overhauling examples where they're continuously regenerating. They're the most demanding type of applications. There's an enormous amount of energy. Dynamic braking and regenerative braking are the methods to use. Regenerative braking is the most sophisticated means of braking, and it costs the most. It's used typically just for overhauling regenerative applications, and it requires additional hardware or active front end, acronyms AFE, in addition to the drive. So if you do run across an application, you need to size a brake resistor. How do you do that? You can sit and read PFlex AT001 PowerFlex Dynamic Braking Resistor Calculator. It's got all kinds of formulas, and you can sit and go through that and figure out inertias and everything needed. But ultimately, you can call us, or you can call one of our vendors, Power Ohm or Post Glover, which is ENCOMPASS partner, and give them the horsepower. But what you'll need to know is the minimum ohm value of the VFD. And you basically get that by taking the manufacturer, the voltage and horsepower of the VFD. And I have an example a little bit later, but that's all included in our manuals. So you want to have the minimum and the maximum ohm value. Wattage is determined by the application, whether it's a braking or overhauling, the duty cycle, and the horsepower of the VFD. Choosing the correct wattage is important. Otherwise, you can overheat the resistor. And duty cycle is usually stated as a percentage. However, the actual times on and off can be used to offer the optimal resistor package. If you call me or any of our drive specialists, give us a percentage, but it's better to give us the time on, time off. So again, if you give us the time off and time on, it gives us a better view of what the application needs, and we can size the resistor better. I put a couple examples here. This first one being a 25%. But if you look, it's actually giving you the seconds or the time that it needs to break. And ultimately what happens is the 2000 peak watts, and for breaking, you get to multiply that by 50% because it's a breaking application. And then you multiply it by the duty cycle or time on, time off, and you come up with a watts value of 250. The same 25%, but an overhauling load, you don't multiply the 2000 peak watts times 50. You multiply by just the 25% duty cycle, and you come up with a 500 watts value, which is twice what you need. If I go back, you'll see that that's the braking duty cycle only needed 250 watt resistor, whereas an overhauling load where the motor is being pushed for that time is double or 500 watts. So back to getting the minimum value and what you need to know to call us or we can help you with. The top example is from the 520 series technical data guide. And you can see in the table, it shows the minimum resistance of the drive with the horsepower rating. And then the bottom one shows the 750 series technical data guide. And it shows the minimum resistance needed and the maximum current needed that you can put through that IGBT. This, I took a snapshot. This is actually a post-Glover table, and they have a catalog designed specifically for our drives. And you can see that on the left side here, they have the horsepower rating, whether it's normal duty or heavy duty. They have the minimum resistor ohms. They have braking torque, 3 different values. You can have 100%, 122%, or 132%. And then when you start looking at the part numbers, there's that 5% braking. And if you think of the examples I gave, the 250 watt braking versus the 500 watt overhauling, you can see that there a 5% braking is what you would need for a braking application, and a 2.5% for the overhaul, and that carries all the way through. If, just as a reference, a lot of times we get a call, I need a brake resistor for this drive, and I don't have any application information. In order so that I don't glow it red, I have to look at either 50% or 100%. So I have to ask about the application to figure out what type of braking we need and just how many watts and everything we need on there. So I wanted to throw this in because we get asked this question a lot. When you install a brake resistor, and it mentioned earlier you want to prevent it from overheating, most brake resistors come with at least a thermostat, and some we can actually get with temperature protection. If you install an external brake resistor on one of our drives, the recommended way is to take the thermostat through a contactor and kill the AC input to the drive. And they do that. They recommend this because in the event that the brake IGBT within the drive, that 7th IGBT, if that shorts, which is not common, but if it shorts, it can keep just putting current out onto the brake resistor. And then on the left here, that's actually from the post-Glover installation manual. Resistors should not glow red under normal operating conditions. They should get warm, but not glow red. And then they have a note in there, if the resistors do glow red, please contact post-Glover. A little bit of application, I had a centrifuge I was working on, and Rockwell has a centrifuge dynamic brake calculator, and I used it in the pretty early stages. And I sized up the resistor. I got the resistor, and it was a 200 horsepower motor. And they got it running. But then I got a call the next day. Should that thing be glowing red? And I was like, what do you mean, the resistors? They said, no, the entire case. Went back and there was a error in the centrifuge resistor calculator, and it was like a quarter of the dynamic break size or dynamic resistor that should have been used. So we corrected it. So they're not supposed to glow red, and neither is the case. The pros and cons of a dynamic break resistor, the advantages, they're the simple, effective method, and they are a low upfront cost compared to some of the other options. The disadvantages are the heat dissipation from the resistor banks may affect other components. Careful placement of the resistors needs to be considered. And heat affects all the components, including the resistors. Excessive or prolonged heat may damage components. For this reason, the duty cycle should be limited. And power purchased from the utility is lost to heat. It could have been recycled with another method. Excuse me. So that's the dynamic break resistor and how we handle it with resistors and chopper units. I'm going to go into a little bit on the active front end, or AFE now. The typical VFD uses a 6-pulse rectifier bridge, and they have either diodes or SCRs on the converter or front end to do the AC to DC power conversion. And this is just a very simple block diagram showing that. A regenerative or active front end uses back-to-back inverters isolated by the DC bus. And generally there's an LCL filter on the input. And you can see instead of having that SCR or diodes on the converter, we have another IGBT on the front end of the drive. An active front end converts the regenerative energy produced by the motor and connected load to electrical energy and returns the excess electrical energy back to the power source. And an AFE does both motoring and regenerative power while maintaining near unity power factor. Some of them are 0.99, and we've actually got one that is almost 1.0. Because of that LCL filter that we require on the front, they are IEEE 519 compliant. And so that way the harmonics is reduced to within those levels. It eliminates the need for braking resistors and cooling equipment, associated wiring, labor installation, and the maintenance costs. They're useful in applications requiring overhauling and high inertia loads. A couple examples are crane and hoist, and when you do a lot of braking during loading, and centrifuges, which are very high inertia loads. Recovering motor braking energy, regenerative drives help reduce energy consumption and are significantly more energy efficient than resistive braking. Again, when you're using a dynamic brake resistor, you're taking that extra energy and blowing it off as heat. So I threw a quick example of our active front end, or AFE. We call it 755 TR. We have it available from 10 to 6,000 horsepower. And I showed a quick diagram of our frame 5 there. And you can see the LCL filter, which is 5 that's included there. It's all one enclosure. That's good. From our frame 5 is from 10 to 75 horsepower at 480. And we go from 200 or 75 to 200 with a frame 6, which is shown here. And then this is a frame 7 NEMA 1 and a frame 7 NEMA 12. And I just wanted to show that's our dimensions. So if you've got something that's regenerating a lot, active front end may be the way to go. And we go all the way up to bigger horsepowers. And I just wanted to show the frame 8, 9, 10, and 11. We go all the way up even higher into 12, 13, 14, all the way up to 15. Another way of handling the regenerative energy, if you don't want to do dynamic brake or put that energy back onto the power grid all the time is common bus. And this drives AT002 manual. It's 162 pages of fine reading material. It goes into great detail about all these different types of configurations of common bus. I highlighted 3 in red that I'm going to show examples of. But in that manual, once you pick your configuration that you're going to use based on your application, it shows you the fuse sizes, shows you the different drive horsepowers and sizes that can mix and be put on the common bus. So this is an example of shared DC bus, also referred to as piggyback. And it's a standalone VFD as the converter, and additional common DC bus drives. And that's why it's called shared DC bus. And a system with multiple motors, some may be regenerating while others are motoring. Common bus allows the regenerating drives to share power with the motoring drives, thus reducing the amount of power needed from the grid. Basically what happens is you would size that supply drive, the converter, you would size that to handle the entire motoring application. And the 3 dots here, I can just keep lining up drives here. I have to take into account on my supply drive the full motoring need amperage wise of the application. But once I get everything up and running, if one is always being forced into regen, the other drives can use it. So again, it reduces your need from the grid, and you're not having it drives out there with individual drives with brake resistors blowing off energy as heat. The next one is the shared DC bus, again, piggyback, with a braking chopper thrown in there. And it's the same standalone drive. They're all sharing the DC power when needed. The only difference is you throw a brake resistor if there's instances with the application where you would have the DC bus rising too high. If everything goes into regen, you would actually be able to break it and reduce it that way. And then another form of common bus, another configuration is regenerative bus supply. Again, we're taking an active front end drive or a bus supply and putting it in front. And this configuration is characterized by a PWM controlled IGBT converter for full regen of power to the AC line. The regen bus supply puts energy back onto the distribution system instead of dissipating heat. Configuration provides low AC line harmonics, and if you have a drive lineup, you can meet IEEE 519. And I threw this one in here because we can actually not only power just an AC drive, but if you have a system lineup, we can actually run servo drives off that front end. And when you do have a surge or everything regen, you would put that energy back onto the power grid. The other thing, all these notes, every one of these examples I've shown of the configurations are from that drive T00. And you can see all the notes and special bus requirements, things in common bus. Hey, Julie, can you mute whoever that is making noise? One of the things that happen in common bus, you may have you may have a larger size drive and some of our small drives, and depending on whether we use diodes on the converter or we may use SCRs, there's different requirements. There's even different DC bus inductance. All that has to be taken into account. And in that manual, if you have an application that you think common bus applies, we can sit down and go over, okay, you need this 25 horse, you also need this 150 horse. It tells us exactly which ones and any special requirements needed. Sometimes with common bus, like in this example, you can see I just have fuses there on my DC bus. Other ones I need diodes to control the current flow. Again, it depends on the mix. If they're all the same size drive, it's relatively simple. When you start mixing the matching horsepowers, then you have to take into account quite a few things. But again, it's all covered in that common bus manual. The good thing about common bus and a drive system, you can coordinate multiple motors. And again, it's regenerative. If you use regenerative common bus, and you can use common bus inverters, some of our drives you can order as AC input, or you can order the drive as a DC input drive. If you know you're going to be using it in a common bus application, you don't need to pay for the extra SCRs or diodes in the converter. You get just the inverter. You can optimize the size of the bus supply. We've got flexibility, combine inverters, bus supplies, different arrangements that you can reduce and optimize floor space, reduce costs. When you got a system like that, you're not doing a bunch of different, you're only dealing with the inverters, and it's a scalable system. And I'll show our solution for common bus. This is for large horsepower, as you can see, for certain applications, 250 horsepower up to 6,000 horsepower. And what you see here, this is actually the 755 TM. And here in the blue, you see regenerative bus supply. That's the converter section there. It does the pre-charge. It does the LCL filter. And then in the green here, this is the common bus inverters. I can stack multiple converters in there, and I don't need to make up that DC. That's all done in the bus supply. And I have these control pods here. So I basically just configure my inverter, and they've got a bus that's just providing the DC. This is the table of this sizes. Again, we start at 250 horsepower with a TM. We go up to 300 or 3,000 horsepower. And this is the sizes, dimensions, and if you have a common bus application, just give us a call. We can figure it out. I've talked about Post Glover a couple times. There's quite a few ENCOMPASS partners. I listed the three here that I personally deal with the most, and they've got some very knowledgeable people. And Bonitron makes quite a few things to handle. They call it over voltage, and they're geared towards, they make brake transistors, which are choppers. They make actual resistors. They make a common bus supply, which if you want to throw just a common bus and use DC drives, they can. They also have a standalone line regen that you can put on your system if you want to, if you have enough regenerative energy that you want to put that power back on the grid. They have a standalone line regen. Post Glover, as far as I know, does resistor. That's pretty much their specialty. And they're the ones I showed that table from. And they have resistors catalogs for not only Allen Bradley drives, most of the major manufacturers they work with, they have a resistor catalog geared specifically for the drive you're dealing with. And then there's power ohm resistors. They make standalone brake transistors, again, choppers. They also have resistors. They also have a pretty neat little unit. It's called a braking resistor analyzer. If you've got an application, you're getting over voltage fault, or you go into the application knowing you're going to need some braking capability beyond what the drive can do, you put this braking resistor analyzer on, and it will tell you what size resistor you need, and that analyzer can stay on the drive, act as that braking resistor until you get the actual braking resistor delivered. So it's a pretty neat little gadget for figuring out what you need. You don't have to go through and read that sizing calculator and do all that. This device does it for you. And I went through that pretty quick, but overall, that's what I have. And if anybody has any questions, I can't see the chat right now. So if anybody has any questions and you want to ask or haven't been answered, feel free to, and thank you for your time.
No questions. All right, Rick, you must have been very comprehensive.
Yeah, okay.
For everybody on the line, also, if you visit rumsey.com/events, as Rick has listed there, you'll see what the webinar schedule is for upcoming other technical talks. We're calling this maybe the all access series to our Rumsey specialists. I think the calendar is posted into early August, but we just finalized through November. So if you check back today, check back again next week, and you'll see the list of tech topics through November. And with that, if there's no other questions, I think we'll close up for the day. Look for your email, your follow-up email with a little bit of the information Rick mentioned, as well as a copy of the recording and the PowerPoint, probably sometime tomorrow.